Tonight, we're going to visit a place that is already 26,000 years in the past. Every observation we have ever made of the galactic center, every image, every flare, every orbit of every star around the black hole at the Milky Way's heart, happened before modern humans painted the first cave walls. The light from those events has been traveling toward us since before written language, before agriculture, before the oldest civilization we know of. The center of our galaxy is not a place you can observe in real time. It is a memory, a very detailed, very strange memory, full of things we are only now learning to read. And the more carefully we read it, the more clearly we see that the memory is not only about that distant place. It is also about how we came to be the kind of thing that could ask about it. There is a black hole there, 4 million times the mass of our sun. It flares in X-rays daily, flickers in infrared constantly, and is surrounded by young stars that should not exist anywhere near it, and we know none of this as it currently stands. We only know it as it was 26,000 years ago, when its light began crossing toward us. Tonight, we travel to the center of our galaxy and discover what that light has been trying to tell us. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Find a clear night, if you can, one where the sky is dark enough and the air is still enough that you can see the full length of the Milky Way stretched above you. You will notice that it's not uniform. It is brighter in some places and fainter in others. In late summer from the northern hemisphere, there is a particular direction where the band thickens and brightens, where the glow deepens into something that looks almost three-dimensional. That direction is toward the constellation Sagittarius, low in the southern sky. That is the direction of the galactic center. You cannot see the galactic center itself. Nobody can with their eyes alone. What you are looking at is not the center. It is the outer layers of the galaxy, the spiraling arms and their billions of stars, along with the dust and gas that fills the space between them. The actual center, the dense and violent and ancient heart of the Milky Way, is hidden behind all of that. It sits behind approximately 25 magnitudes of what astronomers call visual extinction, meaning the dust between here and there is thick enough that visible light from the galactic center cannot reach your eyes. Not faintly, not dimly, not at all. To understand what 25 magnitudes of extinction actually means, consider this. Each magnitude represents a factor of roughly 2.5 in brightness. Stack 25 of those factors together, and you arrive at a number around 10 trillion. A star at the center of the Milky Way would need to be roughly 10 trillion times brighter than it actually is for a single photon of its visible light to reach you through all that dust. The center is not just difficult to see. It is, in every practical sense of the word, invisible to the unaided eye and to every optical telescope ever built. This is not a minor observational inconvenience. It shaped the entire history of how we came to understand our own galaxy. For most of human history, the Milky Way was simply that, a band of diffuse light. Ancient cultures looked at it, named it, told stories about it. Some of the greatest astronomers of the early modern period tried to map it and came away with incomplete pictures, partly because they were located inside it, and partly because the most important part of it was hidden from them behind a curtain of dust they did not yet know was there. William Herschel, one of the most accomplished observers of the 18th century, attempted to map the shape of the Milky Way by counting stars in different directions and inferring the galaxy's structure from those counts. His method was ingenious and his observations were careful, but it produced a distorted picture because the dust in the plane of the galaxy absorbed the light from more distant stars, making the galaxy appear smaller and more symmetrical than it actually is. Herschel placed the sun near the center of his inferred structure, not because he was careless, but because the dust prevented him from seeing the evidence that would have told him otherwise. The real shape of the Milky Way and the real position of its center only became clear when astronomers learned to see at wavelengths that the dust could not block. It was not until 1931, when an engineer named Karl Jansky was investigating persistent radio interference for Bell Telephone Laboratories, that anyone detected a signal from the galactic center at all. Jansky was not looking for it. He was trying to diagnose noise on telephone lines. The signal he found came from the direction of Sagittarius, steady and repeating, and it puzzled him enough to publish. Most astronomers at the time paid little attention. What Jansky had heard, without knowing it, was the galactic center. Radio waves, with their much longer wavelengths, can pass through the dust that blocks visible light the way a long ocean swell passes through a kelp forest while a ripple is absorbed. The center had been broadcasting at radio frequencies continuously. We simply had not yet built the instruments to listen. The full picture of what lies at the center of our galaxy was not assembled until the second half of the 20th century, and it is still being refined today. In 1974, two radio astronomers detected an unusually bright compact radio source at the precise center of the Milky Way and named it Sagittarius A for the constellation in whose direction it sat. Finer observations revealed a point-like source within it, so luminous and so compact that it had no ordinary explanation. That inner source received an asterisk appended to its name, becoming Sagittarius A star, a notation meaning something worthy of special attention. The asterisk was correct. What we now understand about the galactic center required decades of observation across wavelengths that human eyes cannot see: radio, infrared, X-ray, gamma ray, each one penetrating the dust to a different degree and revealing a different layer of what is behind it. The picture that emerged from all of those layers is one of the most extreme environments our galaxy contains, and one of the strangest places in the known universe. We are going there tonight, but the distance matters before the destination does, and the distance between here and the center of the Milky Way is not simply a large number. It is a territory full of things that deserve attention before we arrive. The number is 26,000 light years. A light year is the distance light travels in one full year, moving at approximately 300,000 kilometers per second. At that speed, light can circle the entire Earth about 7 times in a single second. In 1 year, it crosses nearly 10 trillion kilometers. Multiply that by 26,000 and you have the distance to the galactic center. This is a number that resists comprehension. It is designed to be incomprehensible. The human mind was not shaped to hold distances like this in any intuitive way, because nothing in the environment our ancestors evolved in required it. We can hold the number, we cannot feel it. What we can do is understand what it contains. The Milky Way is a spiral galaxy, meaning it has a central concentration of stars surrounded by a rotating disk in which the stars arrange themselves into sweeping curved arms. Our solar system sits within one of those arms, a region called the Orion Arm, or sometimes the Local Arm, positioned roughly 26,000 light-years from the center. We are not at the edge of the galaxy. The galaxy extends further outward from us than it does inward. But we are in what astronomers consider the middle regions of the disk, in a relatively calm and sparsely populated section of one arm. The territory between here and the galactic center is not empty. This is the first thing to understand about the voyage inward, and it is the thing most people do not instinctively grasp. Space looks empty from Earth because the distances between objects are vast, and because we're accustomed to thinking of space as a vacuum. But vacuum and empty are not the same thing. Between every star in our galaxy there is gas. There is dust. There are molecular clouds, some of them larger than the distance from the Sun to the nearest star. There are stellar nurseries where new stars are forming from collapsing gas right now, at this moment, measured in the light that left them before you were born. There are the remnants of dead stars, expanding shells of gas thrown out by supernovae, neutron stars spinning in the dark, clouds of organic molecules discovered in regions of space that were supposed to contain nothing interesting. The galaxy between Earth and the galactic center is full. As you move inward, crossing the first major spiral arm beyond our own, the stellar density begins to change. Stars become more frequent. The interstellar medium, the diffuse gas and dust that fills the space between stars, becomes richer, more chemically complex, more energetic. Each spiral arm you cross represents a region where stars have been forming for billions of years, where the accumulated products of stellar evolution have seeded the surrounding space with the elements that heavier than hydrogen chemistry requires. Between the arms, the space is somewhat calmer, fewer new stars forming, older stars dominating. The gas thinner, less turbulent. If you were moving at the speed of light on this voyage, you would spend thousands of years crossing each arm, then thousands more crossing the inter-arm regions, then entering the next arm and finding it denser and more active again. Each arm has its own character. Some are richer in young, massive, short-lived stars. Some contain more older stellar populations. Some are denser in molecular gas and therefore more actively star-forming. The Milky Way's spiral structure is not a fixed set of rails, but a dynamical pattern, a density wave propagating through the disk, a region where the orbiting material temporarily piles up and then disperses again, like a slow wave moving through a crowd of people walking in a stadium. The Sun has passed through several of these arms over the course of its life. Each crossing was a period of slightly elevated stellar activity, slightly higher supernova rates, slightly more complex chemistry in the surrounding medium. These crossings may have left detectable traces in Earth's geological and paleontological record in the form of mass extinctions or periods of elevated cosmic ray flux. Whether the connection is statistically robust is still debated, but the principle is clear. The galaxy's structure leaves marks on the planets within it, and the Sun's position within that structure has changed over geological time. By the time you have crossed halfway to the center, the sky has already changed. The night sky as seen from Earth contains perhaps a few thousand stars visible to the naked eye on a clear, dark night. The vast majority of those stars are within a few thousand light-years of us. As you move inward through the galaxy, each unit of distance you cross adds more stars to the sky, more nearby stars, not just more distant ones. The background glow of the galaxy intensifies. The directions between the brighter stars fill in. By the time you reach the inner disk, still thousands of light-years from the center, the familiar patterns of the Earth's sky would be unrecognizable. There would be no true darkness between the stars. The galaxy's own diffuse light would fill the gaps. In the region of the nuclear star cluster, closest in to Sagittarius A, the stellar density reaches levels that have no analogue anywhere in the outer galaxy. Estimates suggest the volume around the nuclear star cluster contains roughly 10 million solar masses of stars within just a few light-years of the center. In our neighborhood, the nearest star to the Sun is about 4 light-years away. Near the galactic center, the average separation between stars may be measured in light weeks or even light days. The night sky from a planet in such a region would be ablaze, not with a moon's worth of light, or even the full moon's worth. With a sky so bright that the concept of night, of true darkness, of a sky with only stars in it, would simply not exist. There would be no darkness there. Not a temporary darkness, not a seasonal darkness. No darkness at all, in any direction, at any time. The combined light of 10 million nearby stars would be the constant background of every moment of every day for every creature that had ever lived on a planet in that region, for as long as stars had been forming there. We have never experienced anything like it. We have no frame of reference for it. But it is, for any planet near the galactic center, simply what the sky is. The voyage inward is not a crossing through emptiness. It is a crossing through increasing fullness, until you reach a place so full, so dense and so energetically active that the ordinary physics of the outer galaxy no longer applies. Consider what the night sky would look like at the halfway point. You are now roughly 13,000 light-years from Earth, 13,000 light-years from the galactic center. You're in the inner disk, somewhere in the region between the normal arm and the far side of the Scutum Centaurus arm, in territory that no spacecraft has ever visited and that exists in our knowledge only through indirect observation. The sky here is not the sky from Earth. There are no familiar constellations because all of the stars that form those constellations are now so far behind you that they have blended into the background. The background itself is brighter. Not dramatically brighter, not yet, but noticeably so. The diffuse glow of the inner galaxy fills more of the sky. The dark patches between the stars are fewer and smaller. There are more nearby bright stars, simply because there are more stars in every direction. You are not yet at the point where the sky is never dark. That comes closer in, but you are in a region that would be clearly recognizable as different from the outer galaxy to any observer with eyes adapted to compare the two. This is a denser, richer, more active region of the Milky Way. The chemistry is richer. The average age of the stellar population is somewhat different. The frequency of stellar events, supernovae, variable stars, stellar interactions is somewhat higher, and inward from here it continues to change. The density continues to rise. The chemistry continues to grow richer. The environment continues to become more energetic, more complex, more shaped by what sits at the center. We will reach that place, but we go there in stages, and the first stage is understanding the wall that hid it from us for so long. Before that wall, though, there is one more thing worth pausing on as we leave the familiar outer galaxy behind. The Sun has been orbiting the galactic center for its entire life. Every star in the Milky Way has been doing the same. The solar system completes one orbit around the galactic center roughly every 230 million years. In the roughly 4.6 billion years since the Sun formed, it has made approximately 20 of those orbits. 20 full laps around the center of the galaxy, each one taking longer than all of complex animal life on Earth. During those 20 orbits, the Sun has passed through several spiral arms, crossed regions of higher and lower stellar density, and experienced the gradual changes in the galactic environment that come with the slow churning of a rotating disk. The Sun is not parked at one address. It is a moving object in a rotating system, and its relationship to the galactic center has been slowly changing for as long as it has existed. The light that left the galactic center at the moment the Sun formed is still traveling. It has not reached us yet. It will not arrive for another roughly 22 billion years. The Sun will be long dead before the light that left the galactic center at its birth ever reaches it. This is what 26,000 light-years actually means, held in time rather than space. Sometime in 1931, Karl Jansky noticed something he could not explain. Jansky was an engineer, not an astronomer. His job was to understand radio interference, the static and noise that disrupted long-distance telephone transmissions. Bell Telephone Laboratories had built him a large rotating antenna on a New Jersey field to help him track down the sources of that interference. Most of what he found was predictable: thunderstorms, nearby electrical equipment, the general electromagnetic noise of a technologically active world. But there was one source he could not account for. It was faint and steady, and it rotated with the antenna in a pattern that matched neither the Sun's movement nor any known terrestrial source. It came from the same direction every day, arriving about 4 minutes earlier each successive rotation, which is the signature of something moving with the stars rather than with the Earth's relationship to the Sun. Jansky eventually identified the source as the center of the Milky Way. He published his finding. The astronomical community's response was largely indifferent. A radio engineer had found a signal from the galactic center, and the people best positioned to follow it up mostly did not. It took a decade for a radio amateur named Grote Rebrett to build his own dish antenna in his backyard in Illinois and produce the first radio maps of the sky, confirming and extending what Jansky had found. By the 1950s and 1960s, radio astronomy had matured into a serious scientific discipline, and the galactic center had become one of its primary targets. What the radio maps showed was not a quiet center. They showed a complex, bright, active region with structure at multiple scales, emitting powerfully across radio wavelengths in ways that demanded explanation. The reason this mattered so much, the reason radio waves were the key that unlocked the galactic center when optical light could not, comes down to physics that is almost beautiful in its simplicity. When light encounters a dust grain, what happens depends on the relationship between the wavelength of the light and the size of the grain. Visible light has wavelengths of roughly 400 to 700 nanometers, and interstellar dust grains tend to be comparable in size to those wavelengths. When a photon of visible light encounters such a grain, it is absorbed or scattered. It does not pass through. Radio waves have wavelengths measured in centimeters, millimeters, or even meters. They are enormously larger than dust grains. When a radio wave encounters a dust grain, the interaction is minimal. The wave passes around the obstacle the way a long ocean swell moves around a pebble on a beach. Infrared light, with wavelengths between visible light and radio waves, falls somewhere in between. Near-infrared wavelengths can penetrate the galactic dust reasonably well, though not as completely as radio waves. This is why when the infrared space telescope era began in the late 20th century, it opened a new window onto the galactic center that complemented the radio view. Between these two windows, radio and infrared, the galactic center was systematically revealed over the second half of the 20th century. Each new generation of instruments brought greater sensitivity and resolution. Each new observation added detail to the picture. By the time the first image of Sagittarius A was captured by the Event Horizon Telescope in 2022, the galactic center had been studied intensively for 7 decades, and it was still producing surprises. The galactic center, invisible to every human eye in all of history, became visible in the late 20th century to the instruments we built to see beyond what our eyes could reach. And what those instruments revealed, beginning in the 1980s and continuing to this day, is a place so far outside ordinary astronomical experience that it required entirely new frameworks to describe. There is a way to appreciate what this history means that goes beyond the science itself. For the entirety of recorded human civilization, roughly 6,000 years of cities, writing, philosophy, and accumulated knowledge, the center of the Milky Way was not known to exist in any meaningful sense. It was behind a curtain. Astronomers could see the Milky Way band, could estimate it was a disk of stars, could begin to map its overall shape by the distribution of stars they could see. But the center was invisible, the most significant structural feature of our own galaxy, the mass concentration that governs the orbital dynamics of every star in the Milky Way. The supermassive black hole, whose past activity shaped the halo gas above and below the entire disk, was simply not available to human inspection. We've had access to the galactic center for less than a century. In the context of human history, that is almost nothing. In the context of what we have learned in that time, it is extraordinary. The dust did not simply inconvenience us. It delayed our understanding of our own galaxy's heart by approximately the entire history of modern science. Everything we know about the galactic center, every fact, every measurement, every image in this entire voyage, was gathered in roughly the last 100 years. We are, in the deepest sense, just beginning. Before the center becomes fully visible, you pass through a region that most people have never heard of but that shapes everything happening near the galactic core. It is called the Central Molecular Zone. The name is dry. The reality it described is not. The Central Molecular Zone is a roughly disc-shaped region of gas and dust extending from the galactic center outward to about 1,000 light-years in radius. It contains an enormous amount of molecular gas, perhaps several tens of millions of solar masses worth, concentrated into a region that is large in absolute terms but tiny by galactic standards. It is one of the most chemically active regions of the Milky Way, containing organic molecules that were discovered there before they were found anywhere else in the galaxy. In the outer galaxy where we live, molecular gas tends to be cold and relatively calm. The temperature of a typical molecular cloud in our neighborhood is around 10 to 20 Kelvin, close to absolute zero. The gas moves slowly. It clumps under gravity, collapses, forms stars, and the cycle continues. This is the familiar version of the interstellar medium, the raw material of star formation operating under conditions that have been well studied and reasonably well understood. In the Central Molecular Zone, this picture does not hold. Gas temperatures there are not 10 to 20 Kelvin. They range from roughly 50 to several hundred Kelvin, and in some regions higher still. This is not a minor difference. A gas cloud that is 100 Kelvin warmer than a comparable cloud in the outer galaxy behaves differently in almost every physically relevant way. It is harder to compress. It resists gravitational collapse more strongly. The physics of star formation changes significantly. The gas turbulence in the Central Molecular Zone is roughly 10 times higher than in comparable clouds in the outer galaxy. The velocity dispersions, meaning the range of speeds at which gas parcels within a cloud are moving relative to each other, are large enough that the clouds appear to be constantly stirred from within. This is not turbulence in the sense of random thermal motion. It is turbulence driven by energy input from the environment, from stellar winds, from supernova explosions, from the outflows of Sagittarius A, from the tidal forces of the concentrated mass at the center. The magnetic field is stronger than in the outer disk, structured differently, and deeply involved in shaping how the gas moves and where it accumulates. Gas clouds in the Central Molecular Zone do not simply drift together and collapse. They are threaded by magnetic field lines that resist compression in certain directions, shaped by the same large-scale vertical field that produces the glowing radio filaments visible in this region. The result is a region of the galaxy where the ordinary recipe for star formation has been disrupted. In the outer galaxy, a molecular cloud that reaches sufficient density will collapse under its own gravity and begin forming stars. In the central molecular zone, the additional turbulence and magnetic pressure resist that collapse. Star formation happens, but at a lower rate than you would expect given the enormous mass of gas available. The gas piles up, the conditions become increasingly unusual. And feeding into all of this from the center is the influence of something that does not exist anywhere in the outer galaxy. The central molecular zone is not just an extreme region of the interstellar medium. It is a region that has been shaped and is still being shaped by the thing that sits at its heart. The chemistry reflects this. Molecular surveys of the central molecular zone have found complex organic molecules in concentrations that are unusual compared to the outer galaxy. Isopropyl cyanide, glycolaldehyde, amino acid precursors. The galactic center is, in one sense, the largest natural chemistry laboratory our galaxy contains, with conditions that drive molecular complexity in ways that cooler, calmer regions cannot replicate. Whether this has any implications for the origin of biological chemistry on Earth is a question that remains genuinely open. The molecules do not need to travel from the galactic center to the solar system directly. What matters is whether the processes that produce them in the galactic center are representative of wider galactic chemistry, or whether they are unique to that extreme environment. The answer is not yet known. The central molecular zone contains several giant molecular clouds that are among the largest and most massive objects of their type in the entire galaxy. The cloud known as Sagittarius B2, located roughly 400 light-years from Sagittarius A, is one of the most massive molecular clouds in the Milky Way and one of the most active sites of massive star formation currently known. It has been a particularly productive site for molecular spectroscopy, the technique of identifying molecules by the specific frequencies of light they absorb or emit, and has yielded detections of dozens of molecular species, some of them directly relevant to prebiotic chemistry. Sagittarius B2 is, in a sense, a chemical factory operating at the edge of the most extreme region of our galaxy. The conditions there, warmer, denser, more energetically driven than typical outer galaxy molecular clouds, produce a molecular richness that has no close equivalent in our neighborhood. You are getting closer to it. The gas around you is warmer than it should be. The magnetic field is stronger than it should be. The chemistry is richer and stranger than anything in the outer galaxy. None of this is happening by accident. It is happening because the center is not a passive place. It produces energy. It produces radiation. It produces outflows. And all of those things leave their marks on the material surrounding it. As you move inward through the central molecular zone, the density increases. The star formation activity changes character. The region becomes more complex, more layered, and the thing at the center becomes increasingly difficult to ignore, not because it is loud, though it is, but because its influence is written into every cloud and every filament and every heated column of gas you pass through. The door is getting closer. What is behind it has been shaping the room you are standing in for a very long time. Now consider a problem that has troubled astronomers for decades and has still not been fully resolved. Stars form from gas clouds. This is the basic mechanism of stellar birth in the universe. A cloud of molecular gas becomes dense enough through gravity and the right conditions that it begins to collapse under its own weight. As it collapses, it heats. A core forms, ignites nuclear fusion, and a star is born. The process requires cold, dense gas in a region where the external forces acting on that gas, turbulence, magnetic pressure, the tidal gravity of nearby massive objects, are not too strong to prevent collapse. Near the center of the Milky Way, the tidal gravity of the central black hole is immense. Within a certain radius of Sagittarius A, that tidal force is strong enough to tear apart any molecular cloud that drifts too close before it can collapse into stars. The math is relatively straightforward. You can calculate the radius within which tidal disruption prevents star formation, and astronomers have done exactly that. The problem is that when they looked at the region inside that radius, they found stars. Young ones. Massive ones. Stars whose age astronomers could estimate from their properties and whose estimated age place their formation within the last few million years, inside the region where formation should be impossible. These stars are not ancient relics that migrated inward over billions of years and just happen to be orbiting the black hole now. They are genuinely young, recently formed, and they are right where they should not be. The population includes two main groups. One is a disk of massive, hot, young stars orbiting Sagittarius A at distances of roughly a tenth to a few tenths of a light year. These stars are not orbiting at random. They are orbiting in what appears to be a coherent structure, suggesting they form together from the same body of gas. The other population, found closer in, consists of the so-called S stars, a group of stars orbiting so close to the black hole that their orbital periods are measured in years rather than centuries. One of these S stars, designated S2 or S02, completes a full orbit around Sagittarius A every 16 years. Its closest approach takes it to within roughly a few light hours of the black hole. A few light hours is approximately the distance from the Sun to Uranus. Think about that. This star swings around an object containing 4 million solar masses at a distance comparable to the outer reaches of our solar system, and it does it once every 16 years. By any human measure of time, that is fast. How the S-stars came to be where they are remains debated. One leading idea involves binary star systems, pairs of stars orbiting each other, which drifted too close to Sagittarius A. When a binary passes very close to the black hole, the gravitational interaction can be violent and sudden. The black hole captures one member of the pair into a tight orbit around itself, and the other member is flung outward at extreme velocity. In this picture, some of the stars currently orbiting Sagittarius A are stars whose companions were ejected from the galactic center millions of years ago and are now flying through the outer galaxy. For the massive young stellar disk further out, the leading explanation involves gas clouds that somehow survived the tidal forces long enough to collapse. The mechanism for this is not fully understood. One possibility is that the gas clouds fell in quickly enough on radial orbits that the tidal forces did not have time to disrupt them before collapse could begin. Another involves the gas being compressed by shocks from other infalling material. Neither explanation is considered fully satisfactory by the researchers working on the problem. The young stars near Sagittarius A carry a name in the astronomical literature that captures the paradox well. They are sometimes called the paradox of youth. The name acknowledges that their existence in this location, by everything our theory of star formation predicts, should not be possible, and yet there they are, completing their orbits, aging at the same rate as stars anywhere else in the galaxy, indifferent to the theoretical problem they pose. What matters for this voyage is the deeper point. The galactic center produces stars that should not exist, by mechanisms that are still being worked out, in the immediate gravitational shadow of a 4 million solar mass black hole. The physics of the center has not finished surprising us. The young stars circling Sagittarius A are not decoration. They are evidence that the center operates by rules we have not completely learned to read yet. The black hole lies just ahead. And now, after all this approach, it is time to face it directly. But before we do, it is worth sitting with what the young stars have already told us. They exist in the wrong place. They orbit at the wrong distances. Some of them are moving on orbits so close and so fast that they probe the very edge of what general relativity predicts in strong gravitational fields. The S-stars have allowed astronomers to test Einstein's general theory of relativity in the vicinity of a real supermassive black hole, under conditions that no laboratory on Earth could ever replicate. Measurements of S2's orbit have confirmed the predicted gravitational redshift, the slight shift in the frequency of light as it escapes from a strong gravitational field, to high precision. They have confirmed the precession of the orbit, the slow rotation of its long axis in a direction consistent with general relativistic predictions. The galactic center is not merely an astronomical curiosity. It is one of the best natural laboratories we have for testing fundamental physics in extreme conditions. Every orbit of S2 around Sagittarius A is a test of our most successful theory of gravity, carried out at a scale that dwarfs anything human technology could construct. The fact that these stars exist at all, the fact that they are young and close and fast, means that the galactic center has been giving us tools we did not expect to find there. in a place where we expected only chaos. Before you reach Sagittarius A itself, there is something else you would encounter that no description quite prepares you for. The galactic center contains structures that are visible in radio wavelengths and that have no counterpart anywhere in the outer galaxy. They are long, thin, glowing filaments of radio emission. Some of them stretch for tens of light years, while remaining only a fraction of a light year in width. They appear to be oriented perpendicular to the galactic plane, standing roughly vertical against the flat disk of the Milky Way. And they are not random. They have structure, regularity, and geometry that immediately suggests something organized is behind them. Astronomers first identified these structures in 1984, when radio observations at high resolution revealed the brightest collection of them, a complex now called the Galactic Center Radio Arc. What the observation showed was a system of parallel, extremely straight narrow filaments running perpendicular to the galactic plane, brighter than any comparable structures seen elsewhere in the galaxy. The filaments glow because of a process called synchrotron radiation, when electrons moving at close to the speed of light spiral along magnetic field lines. They emit radiation at radio wavelengths. The brightness and spectral properties of the filaments tell astronomers both the energy of the electrons producing the emission and the strength of the magnetic field guiding them. What the analysis shows is striking. The magnetic field along these filaments is estimated to be somewhere between 100 and several hundred microgauss, and in the strongest cases perhaps approaching a milligauss. To put this in context, the typical magnetic field in the outer galactic disk is a few microgauss. The filaments of the galactic center are threaded by magnetic fields that are, in some estimates, 100 times or more stronger than what you would find in our neighborhood of the galaxy. More than that, the magnetic field orientation at the galactic center appears to be fundamentally different from the outer disk. In the outer galaxy, magnetic fields tend to follow the galactic plane, running roughly along the direction of the spiral arms. In the galactic center, the large-scale field appears to run perpendicular to that, standing vertical against the disk. The filaments trace those vertical field lines with a precision that makes them look, in radio images, like the galactic center has been laced together with glowing wire. Hundreds of these filaments have now been catalogued, scattered throughout the central few hundred light years of the galaxy. The brightest are visible in early radio maps. The fainter ones were only fully revealed by modern interferometric radio telescopes with the resolution to separate them from the background emission. Nobody fully understands why the galactic center has this magnetic architecture. The leading ideas involve the activity of Sagittarius A and the outflows it produces, which may have shaped the large-scale field over millions of years. The gas dynamics of the central molecular zone, with its unusual turbulence and velocity structure, may also play a role. What is clear is that the galactic center is not magnetically disorganized. It has structure. The outer galaxy's magnetic field runs parallel to the disk, following the spiral arms in a loose, tangled way. The inner galaxy's field runs perpendicular to all of that, organized at right angles to the plane in a way that has no obvious counterpart in the outer regions. The filaments are the visible expression of that organization, like frost patterns on glass that trace an underlying geometry you would not have guessed from the outside. When you look at a radio image of the galactic center, you are looking at a place whose internal architecture is visible in a way that the outer galaxy's is not. The outer galaxy hides its magnetic field. The inner galaxy traces it in light, and these structures connect physically to the thing they encircle. The filaments run toward the center. The magnetic field lines they trace have one of their endpoints at or near the source of the energy that fills them with fast electrons. Sagittarius A is not simply surrounded by these structures, it is, in some sense, responsible for them. Everything described so far has been approach. Now we arrive. Sagittarius A is not the largest black hole in the universe. It is not even the largest known black hole in our local group of galaxies. The black hole at the center of the Andromeda Galaxy, our nearest large neighbor, is thought to be considerably more massive. The black hole at the center of the giant elliptical galaxy, M87, the one for which the first event horizon image was captured in 2019, contains roughly 6.5 billion solar masses, more than 1,000 times the mass of Sagittarius A. By the standards of supermassive black holes, Sagittarius A is relatively modest, but it is ours. It is the closest supermassive black hole to Earth by an enormous margin, and that proximity has allowed astronomers to study it with a precision that is impossible for any other galactic nucleus. The mass of Sagittarius A is not estimated from statistical arguments or indirect proxies. It has been measured directly from the orbital mechanics of individual stars that astronomers have been tracking for decades. The measurement works like this. If you observe a star orbiting an invisible mass, and you can determine the shape of the orbit and the time it takes to complete, you can calculate exactly how much mass the star is orbiting. This is the same principle that governs the calculation of the Sun's mass from the Earth's orbit, or the Earth's mass from the Moon's orbit. Gravity and orbital mechanics are connected by equations that are extraordinarily well tested. Beginning in the 1990s, two independent research groups, one in Germany led by Reinhard Genzel and one in the United States led by Andrea Ghez, began tracking individual stars near the galactic center using infrared telescopes equipped with adaptive optics systems that could compensate for the blurring effect of Earth's atmosphere. Over the following decades, they tracked more than 100 stars in the region and measured their orbital parameters precisely. The star designated S2 provided the clearest case. Its full orbital period of approximately 16 years was directly observed. Its closest approach to the central mass, measured in detail, placed it within a few light hours of Sagittarius A. The orbital data required a central mass of approximately 4 million solar masses, concentrated into a region smaller than our solar system. No known astrophysical object other than a black hole could account for this combination of mass and compactness. In 2020, Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics for this work. Not for a theoretical prediction, not for an indirect detection, for directly observing the motion of individual stars around the black hole at the center of our own galaxy, and measuring its mass to high precision. The Nobel Prize was awarded for work that began with patient observation over many years, tracking faint points of infrared light shifting position against the galactic center background, building up orbital solutions one data point at a time. It is among the most careful pieces of astronomical measurement in the history of the field. By the time the prize was awarded, the mass of Sagittarius A was known to a precision that would have been considered impossible 30 years earlier. But measurement was not the only milestone. In May 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A itself. The Event Horizon Telescope is not a single telescope. It is an array of radio observatories spread across multiple continents, coordinated to observe simultaneously and combined through a technique called Very Long Baseline Interferometry. The effective diameter of this virtual telescope is approximately the diameter of the Earth, giving it an angular resolution sufficient to see the shadow of a black hole 26,000 light-years away. The image shows a ring of glowing gas surrounding a dark central shadow. The ring of light is gas heated to extreme temperatures as it falls toward the event horizon. The shadow at the center is the event horizon itself, the boundary from within which nothing, not light, not information, not any physical influence, can escape. The event horizon of Sagittarius A has a radius of roughly 12 million kilometers. This is about 17 times the radius of the Sun, or a little larger than Mercury's orbit around the Sun. An object whose mass would take 4 million suns to equal is contained within a radius that you could fit inside the inner solar system. What makes this image different from any other in the history of astronomy is its subject. Every previous image of every astrophysical object ever taken shows something you are not part of: a distant nebula, a planet orbiting another star, a galaxy billions of light-years away. The image of Sagittarius A is an image of the object at the center of the galaxy you live in. It is a photograph of the gravitational anchor around which every star in the Milky Way, including the Sun, is orbiting. You have been orbiting this thing your entire life. So have every one of your ancestors going back to the beginning of the human lineage. So have every organism that ever lived on this planet, for as long as the planet has existed. The galaxy has been turning around this dark center for billions of years. In 2022, for the first time, we took a picture of it. The image is not what most people imagine a black hole to look like. It does not show an obvious hole in space. It shows a ring of warm orange and reddish light, somewhat irregular and asymmetric. with a darker region at its center. The ring is the glowing gas heated to extreme temperatures as it spirals toward the event horizon. The darker region at the center is the shadow of the event horizon itself, the area from which no light can escape. The image is blurry by the standards of everyday photography. The angular resolution required to see the shadow of a black hole 26,000 light-years away through the full depth of the galactic disk stretched the Event Horizon Telescope array to its limits. But it is unambiguous. The ring is real. The shadow is real. The size and shape match the predictions of general relativity for a black hole of exactly the mass that the S-star orbits had already measured. Two independent measurements, two completely different methods, separated by decades of observation, pointing to the same object, confirming each other's findings at the level of precision that defines the best work in science. You are now as close as this voyage will take you. The object ahead emits no visible light. The glowing ring around it is material in its final approach, heated to temperatures of billions of degrees as it spirals inward. The shadow at the center is not a gap or an absence. It is a region from which information cannot exit. Whatever falls past that boundary does not return, not as matter, not as signal, not as any message that could reach the rest of the universe. For a moment, this is what the center of our galaxy looks like. Everything we know about this object was learned in the last 100 years. The mass, measured from stellar orbits over 3 decades of patient observation. The flaring behavior, detected by X-ray and infrared telescopes over the past 2 decades. The image itself, released in 2022 after years of data collection and processing by the Event Horizon Telescope collaboration. The Fermi Bubbles above and below the disk, discovered in 2010 from data that had been available for years before anyone recognized the structures for what they were. A century is nothing on the scale of the galaxy. The Milky Way has been rotating for 13 billion years. Sagittarius A has been sitting at its center for at least as long, exerting the gravitational influence that gives the galaxy its shape. Consuming material in episodes separated by millions of years of relative quiet, building and releasing energy on timescales that have nothing to do with human civilization. We arrived late. We brought very small instruments, and yet we have, in this brief window, assembled a picture of the galactic center that allows us to understand not just what it looks like, but how it behaves, what it has done, and what it might do. That is not nothing. That is one of the more significant things our species has accomplished in its brief time here. The black hole you see today is unusually quiet. Unusually is the right word. Compared to the central black holes of most other galaxies we can observe, Sagittarius A emits very little energy. Its luminosity is roughly 100 million times lower than what you would expect for a black hole of its mass that was actively consuming material at a high rate. Most of the gas that could in principle be falling into it is not. The accretion, the process by which a black hole pulls in surrounding material and converts some of its energy into radiation, is running at an extremely low level compared to what the mass of Sagittarius A could sustain. Astronomers call this state radiatively inefficient accretion. The black hole is eating, but barely, and it is converting very little of what it eats into the kind of luminosity that active galactic nuclei are known for. But quiet does not mean still. Beginning in 2001, the Chandra X-ray Observatory detected X-ray flares from Sagittarius A, brief brightenings that lasted roughly an hour each and repeated roughly once per day. These flares were coming from material heated to extreme temperatures in the innermost region of the accretion flow, the region closest to the event horizon. They were small by active galaxy standards, but they were real, repeating and measurable. In 2023 and 2024, a research team used the James Webb Space Telescope to monitor Sagittarius A in infrared wavelengths over a total of 48 hours of observation, conducted across multiple sessions spanning a year. What they found exceeded their expectations. Sagittarius A was producing 5 to 6 large infrared flares per day, accompanied by constant lower-level variability that never fully subsided. The accretion disk was not flickering occasionally. It was churning continuously, brightening, dimming, brightening again, producing major bursts at irregular intervals with no discernible pattern. The researchers described the behavior as constantly changing, bubbling brightness, punctuated by sudden major bursts that appeared without warning and subsided again over the following hours. Each of those large flares represents an energy release that, were it coming from a source near Earth, would be catastrophic by any human measure. A single large flare from Sagittarius A releases more energy in roughly an hour than our Sun produces in thousands of years. And there are several of them every day. That sentence is worth rereading slowly. More energy in an hour than the Sun produces in thousands of years, several times per day. From a black hole that astronomers describe as quiet, the scale difference between what we mean by quiet at the galactic center and what we mean by quiet in everyday life is the kind of gap that the human mind tends to close too quickly. We hear the word quiet, and we imagine something calm, something manageable, something close in character to silence. Sagittarius A in its quiet phase is producing continuous, irregular bursts of energy at a rate that has no analog in our solar system. What we call quiet is entirely a function of distance and of comparison with more active black holes elsewhere in the universe. By any standard that does not involve other supermassive black holes, the center of our galaxy is continuously active, continuously energetic, and continuously producing radiation at scales that dwarf anything in our stellar neighborhood. Sagittarius A is not sleeping, it is restrained. And the evidence that its restraint has not always been this tight is written in the sky in structures that took us decades to recognize. In 2010, scientists analyzing data from the Fermi Gamma Ray Space Telescope discovered something that had been hiding in the data, not because it was faint, but because it was so large that identifying it required looking at the sky in a particular way. Extending from the galactic center, north and south of the galactic plane, are two enormous structures of gamma ray emission. They are roughly spherical in shape, with surprisingly sharp edging. Each one extends approximately 25,000 light-years above or below the galactic disk. Together they span a total height of roughly 50,000 light-years, which is comparable to the diameter of the entire Milky Way's visible disk. These structures are called the Fermi Bubbles. Nothing in the outer galaxy produces structures like this. The Fermi Bubbles are not a gradual diffusion of radiation outward from the galactic center. They have well-defined edges that suggest they were created by a single energetic event or a period of sustained high activity that drove material outward from the galactic center in both directions at once. The symmetry is striking. One bubble above the plane, one below, similar in size and shape, centered on the same point. The most widely supported interpretation is that the Fermi Bubbles were created by a past episode of intense activity from Sagittarius A, during which the black hole was consuming material at a far higher rate than it does today, and producing a powerful outflow that propagated north and south through the halo gas surrounding the galaxy. The timing of this event is estimated, based on the properties of the bubbles, to have been somewhere between 1 and several million years ago, though the exact date is not settled. 1 million years ago is recent in cosmic terms. 1 million years ago, the early members of our genus Homo were already walking the Earth. The creatures who would eventually become anatomically modern humans were already present in some form on the African continent. Whatever Sagittarius A did that created the Fermi Bubbles happened while our distant ancestors were alive, breathing, moving across landscapes, and experiencing a night sky that would have been visually indistinguishable from ours today. The bubbles they produced extended 25,000 light-years into space above and below the galaxy. The energy content, estimated from the gamma ray emission and the properties of the gas within them, is staggering. Current models suggest the event that created them released more energy than hundreds of thousands of supernovae combined. And today, we call Sagittarius A quiet. The gap between those two descriptions, quiet and capable of releasing the energy of hundreds of thousands of supernovae within the last few million years, is the gap the Fermi Bubbles exist to illustrate. They are not the remnant of some ancient, long-past era of galactic violence that bears no relationship to the present. They are 1 million years old. On the scale of the galaxy's 14 billion-year history, that is a fraction of a percent. The event that created the Fermi Bubbles was, in cosmic terms, recent enough that its direct effects on the galaxy's surrounding gas are still clearly visible. The edges of the bubbles are still sharp. The gas within them is still hot compared to the halo gas outside. The structures are still expanding outward, slowly at velocities that astronomers can measure. There is a related structure, somewhat larger and potentially older than the Fermi Bubbles, discovered in X-ray wavelengths and called the E-Rosetta Bubbles, which extends even further above and below the galactic plane. The two sets of structures may represent different episodes of activity from the galactic center, each leaving its trace in the halo gas, stacked one inside the other, like Russian dolls of different vintages. What the Fermi Bubbles and related structures tell us is that the galactic center's activity is episodic. It is not continuous at a fixed level. It cycles between periods of relative quiet and periods of intense output, and the transitions between these states are driven by how much gas is available to the black hole at any given time. When gas supply increases, accretion increases, luminosity increases, and the effects propagate outward. When the gas supply falls again, the outburst subsides, and the remnants of the active phase are left imprinted on the surrounding material. We happen to be living in a quiet phase. The Fermi Bubbles are not a warning. They are a record. But records are also evidence that the thing they record is real and repeatable, and that the current quiet is not a permanent state. The black hole you observed a few moments ago, quiet and flickering daily with modest flares, has another face. The Fermi Bubbles are that face, frozen into structure, still expanding, still marking the sky above and below the galaxy that contains us both. The galactic center is extreme in every measurable way. We have established that. But the meaning of that extremity extends beyond the physics of gas and magnetic fields and black hole accretion. It extends to the question of whether the region around the center, or anywhere in its extended influence, could ever have been hospitable to life as we understand it. The answer, based on current astrophysical modeling, leans toward no, at least within a certain radius and during certain periods of history. Consider what a planet would experience in the inner few thousand light years of the Milky Way. Stellar density is dramatically higher there than in the outer galaxy. More stars per cubic light year means more potential sources of radiation from stellar flares, from stellar winds, from supernovae. Supernovae, the explosions that occur when massive stars die, release enormous quantities of high-energy radiation and accelerate cosmic rays, which are charged particles moving at near light speed. In the outer galaxy, a planet might experience a supernova within a few hundred light years every few 100 million years. In the inner galaxy, that rate is substantially higher, and the distances involved are smaller. The radiation environment for any planet in the inner galaxy is considerably more intense than what Earth experiences. Then there is the direct influence of Sagittarius A itself. During the active phase suggested by the Fermi Bubbles, the black hole was producing X-ray and extreme ultraviolet radiation at rates far higher than today. Research published in scientific literature has modeled the effect of this radiation on hypothetical Earth-like planets at various distances from the galactic center. The conclusion suggests that during the peak of an active phase, the radiation levels at distances of several thousand light years could have been sufficient to strip planetary atmospheres comparable to Earth's. Not immediately, not in a single catastrophic burst, but over the timescale of the active phase, which may have lasted hundreds of thousands of years. The cumulative effect on atmospheric chemistry, on the ozone-equivalent layers that protect planetary surfaces from ultraviolet radiation, would have been severe. There is also the question of orbital stability. In regions of high stellar density, gravitational encounters between passing stars are more frequent. Over billions of years, a passing star at close enough range can perturb the outer region of a planetary system, altering the orbits of comets and distant bodies in ways that could drive them inward. The geological and fossil record on Earth shows evidence of mass extinctions connected to periodic increases in impact flux. In the inner galaxy, where stellar encounters are more common, the equivalent disturbances to planetary systems may be more frequent, reducing the long periods of relative stability that seem to have been important for life's development on Earth. This does not mean the inner galaxy is completely sterile. There may be condition-specific orbital configurations, strong planetary magnetic fields, atmospheric compositions that resist stripping better than Earth's planets around stars that happen to be in relatively protected orbits, that would allow some form of life to persist even in a more intense radiation environment. Biology is resilient in ways that often exceed predictions. Single-celled life, in particular, has shown a capacity to survive in conditions that no biologist would have considered plausible before the discovery of extremophiles in the late 20th century. The statement is not that life is impossible closer to the galactic center. It is that the conditions that allowed life on Earth billions of years of stable surface chemistry with a relatively calm radiation environment are considerably less likely to be sustained in the inner galaxy than in the outer regions where we live.